প্ৰিয় শ্ৰোতা, আজি ৰেডিঅ' ক্লাছৰুমত উপস্থিত আছে গোৱালপাৰা মহাবিদ্যালয়ৰ পদাৰ্থ বিজ্ঞান বিভাগৰ সহকাৰী অধ্যাপিকা ডক্টৰ Yoshiko Bailung। বাইদেউ, আপোনাক আমাৰ ষ্টুডিঅ'লৈ বহুত বহুত স্বাগতম।
Thank you. A very good morning to all the students out there. Today, I'm going to talk about nuclear transformations, which is a small but the most significant part of nuclear and high energy physics. Nucleus is nothing but the central positive core of an atom. Out of all the four fundamental forces that exist in the universe, that is the gravitational, electromagnetic, strong nuclear force and the weak force, the strong nuclear force is the strongest one. Out of these four forces, every common people are aware about the gravitational force. It's the force that holds us to this earth. Not only us to the earth, but every object in this universe is attracted to every other object by the gravitational force. It holds the earth and other planetary bodies to the sun. So we can just imagine how strong this force is. But interestingly, out of all the four forces, gravitational force is actually the weakest one. The strongest one here is the strong nuclear force, which is 10 to the power 39 times the gravitational force. That is, you put 39 zeros after 1. That much amount stronger is the strong force than the gravitational force. Now, this strong force holds the constituents of the nucleus. When we say constituents of the nucleus, we mean the composition. That is, of what the nucleus is made up of. Protons and neutrons together form the nucleus, and one proton, which is positively charged, and one neutron, which is neutral, together is called one nucleon. So it's clear that the nucleus is positively charged due to the presence of positively charged protons. Now this is known that electrostatically, like charges repel each other and unlike charges attract. To hold the nucleus, in spite of the repulsive forces of the protons, there exists this strong attractive force, which is the strongest one in the whole universe. Now, despite the strength of this strong force that holds the nucleons together to form an atomic nucleus, many nuclides are unstable and spontaneously change into other nuclides by radioactive decay. This is what we call nuclear transformations. Actually, all nuclides can be transformed by reactions with nucleons or other nuclei that collide with them. In fact, all complex nuclides came into existence in this universe in the first place through successive nuclear reactions, some in the first few minutes after the Big Bang and the rest in the stellar interiors. Now, no single phenomenon has played so significant role in the development of nuclear physics as radioactivity, which was discovered in 1896 by Anthony Becquerel. When Henry Becquerel investigated the then newly discovered X-rays in 1896, it led to the studies of how uranium salts are affected by light. By accident, he discovered that uranium salts spontaneously emit a radiation that can be registered on a photographic plate. He repeatedly studied and found out that this radiation was something new and not X-ray radiation. He was able to show that the radiation consisted of fast charged particles and it could ionize gases. Although this discovery of Becquerel was accidental, he realized its importance at once and explored various aspects of the radioactivity of uranium for the rest of his life. He received the Nobel Prize in Physics for the discovery of spontaneous radioactivity in 1903. In the same year, the other half of the prize was shared with Pierre Curie and Marie Curie in recognition of the extraordinary services they have rendered by their joint researches on the radiation phenomena discovered by Professor Becquerel. Now, why knowing or studying radioactivity is important? Most of the energy responsible for the geological history of the earth can be traced to the decay of the radioactive elements such as uranium, thorium, and potassium isotopes it contains. Our Earth is believed to have come into existence perhaps 4.5 billion years ago as a cold aggregate of smaller bodies. These smaller bodies consisted largely of metallic iron and silicate materials that had been circling the sun. Heat accumulated in the interior of the infant Earth, and this heat was of radioactive origin. In course of time, it led to partial melting. The influence of gravity then caused the iron to migrate inward to form the molten core of today's planet. The lighter silicates rose above to form the rock mantle around the core that makes up about 80% of the Earth's volume. Most of the Earth's radioactivity is now concentrated in the upper mantle and the crust, which is the relatively thin outer shell where the heat it produces escapes and cannot collect to remelt the Earth. This steady stream of heat is more than enough to power the motions of the giant plates. Earth's surface is divided into these giant plates. Mountain building, earthquake, and volcanoes all are associated with these motions of the plates, the motion which is being powered by radioactivity. So you see how important it is. Well, here I'd also like to mention about radiation hazards. The various radiations that come out from radioactive nuclides ionize matter through which they pass. Even X-rays ionize matter. All these ionizing radiations are harmful to living tissue. Well, if the damage is slight, then the tissue can often repair itself with no permanent effect. Now, we tend to underestimate radiation hazards. It's easy because there is usually a delay, sometimes of many years, to see the possible consequences after getting an exposure to such radiations. These consequences include cancer, leukemia, and changes in the DNA of reproductive cells that lead to children with physical deformities and mental handicaps. So you can see to what extent radioactivity can affect. In these examples, physics affecting geography and again, physics affecting biology. Now coming back to know more about what is radioactivity. There exist three main features which are extraordinary from the perspective of classical physics. Number one, when a nucleus undergoes certain decays, its atomic number Z changes, and atomic number is the fingerprint of an element. If Z changes, then the whole element itself changes. Classical physics say that elements are not changeable, which is actually not according to radioactivity. Secondly, the energy liberated during a radioactive decay comes from within the individual nuclei without any external excitation. This was classically not possible until Einstein proposed the equivalence of mass and energy, that is the famous relation E equal to mc square, where some amount of mass can get converted to energy. And thirdly, radioactive decay is a statistical process that obeys the laws of chance. There is no such rule as this cause can lead to this effect or this decay. Classical physics cannot account for such behavior. However, this fits naturally to the regime of quantum physics. After the discovery of radioactivity by Becquerel, other scientists who worked on it were the Curies and Rutherford and his team. Via experiments, Rutherford and his co-workers distinguished three components in the radiations from the radioactive nuclides. They are called alpha, beta, and gamma, which later were identified as helium nuclei, electrons, and high-energy photons, respectively. We will try to know more about all these three radioactive decay. First is the alpha decay. In a nucleus, the attractive forces between nucleons are of short range. That is, the range is of the order of 10 to the power minus 15 meter. You take 1 meter, split it into 10 to the power minus 15. This is the average size of a nucleus. Due to this, the total binding energy, the energy that binds the nucleons in a nucleus, is approximately proportional to its mass number. So what is mass number? It is nothing but the total number of protons and neutrons present in the nucleus. As I have already mentioned before, that the protons inside a nucleus experience the electrostatic repulsive force. This force is of unlimited range, and the energy due to this force is approximately proportional to Z square, that is the square of the atomic number. That means if an element has 82 as the atomic number, Z, then this repulsive energy will be approximately proportional to 82 square, that is 6,724. It's huge. So those which contain about 200 or more nucleons are so large that the short-range nuclear forces that attract and hold them together are barely able to counterbalance the mutual repulsion of their protons. In such nuclei, alpha decay occurs in order to increase the stability by reducing the size of the nuclei. In this decay, the parent nucleus gets reduced to a daughter nucleus whose atomic number reduces by 2 and the mass number reduces by 4. Almost 98% of the energy that is released during the decay is carried by the alpha particle, which is helium nucleus. This energy lies in the range of 1 to 10 megaelectron-volt. Next, we will go to the beta decay. Like alpha decay, beta decay is a means whereby a nucleus can alter its composition to become more stable. There are two types of beta decay, beta positive and beta negative. In beta positive decay, proton gets converted to neutron and a positron gets released. And in beta negative decay, it is the other way. That is, neutron gets converted to proton and an electron gets released. When beta decay was looked into in detail, it was seen that conservation of principles of energy, linear momentum, angular momentum were all apparently violated. In 1930, Pauli proposed a desperate remedy for these violations of the conservation principles. He said that if an uncharged particle of small or zero rest mass and spin half is emitted in beta decay together with the electron, then all these problems get solved at once. This particle was later called as neutrino, which meant little neutral one, the neutrino. It was named by Fermi. So two kinds of neutrinos are involved in beta decay, the neutrino itself and the antineutrino. In beta negative decay, antineutrino is emitted along with electron, and in beta positive decay, neutrino is emitted along with positron. Studying beta decay led to the discovery of neutron basically. Finally, we will move to the third one, that is the gamma decay. A nucleus can exist in quantum states whose energies are higher than that of its ground state, just like an atom. We call those as excited nuclei. Those excited nuclei return to their ground states by emitting photons whose energies correspond to the energy differences between the various initial and final states in the transitions involved. The protons which are emitted by nuclei is of very high energy range up to several megaelectron-volts, and they are named as the gamma rays. I would also like to speak about a very important use of radioactivity, that is radiometric dating. Radioactivity makes it possible to establish the ages of many geological and biological specimens. We will see how. The decay process of any particular nuclide is independent of its environment. So, the ratio between the amounts of that particular nuclide and its stable daughter in a specimen depends on the age of the daughter actually. Greater is the amount of daughter nuclide, older is the specimen. Here, I'd like to elaborate the procedure of knowing the age of objects of biological origin using radioactive carbon. It is the beta-active carbon isotopes, carbon with 6 protons and 8 neutrons. Now, cosmic rays are high-energy atomic nuclei, chiefly protons, that circulate through the Milky Way galaxy. About 10 to the power 18 of them reach the Earth each second. Even now in this room, we are having the cosmic rays. So when they enter the atmosphere, they collide with the nuclei of atoms that come in their path and produce showers of secondary particles. Among these secondary particles, there are neutrons that can react with nitrogen nuclei in the atmosphere to form radioactive carbon with the emission of a proton. If I say about the reaction, then it would go like nitrogen with 7 protons plus 1 neutron will give you carbon with 6 protons and 8 neutrons plus hydrogen atom. The proton picks up an electron and becomes the hydrogen atom. This radioactive carbon has greater number of neutrons, and to attain stability, they undergo beta decay to form nitrogen 14 with a half-life of about 5,760 years. Now, half-life is nothing but a parameter to define after how much time a radioactive element contains half the number of its originally present nuclides. So you can see how steadily radiocarbon decays. Even if the decay occurs, yet the cosmic ray bombardment constantly fill up the supply. A total of probably 90 tons of radiocarbon is distributed around the world at the present time. Shortly after their formation, radioactive carbon atoms combine with oxygen molecules to form the carbon dioxide molecules. Green plants take in carbon dioxide and water, which they convert into carbohydrates in the process of photosynthesis, so that every plant contains some amount of radioactive carbon in it. Animals eat plants and thereby become radioactive themselves. When the plants and animals die, they do not take more radiocarbon atoms, but the already present radiocarbon in their body now actually decays to nitrogen 14. After 5,760 years, they have only one half as much radiocarbon left as they had while they were alive. After 11,520 years, which is 2 times of 5,760, only 1/4 as much remains, and so on and so forth. By determining the proportion of radiocarbon to ordinary carbon, it is thus possible to evaluate the ages of ancient objects and remains of organic origin. This elegant method permits the dating of mummies, wooden implements, cloth, leather, etc. from ancient civilizations as much as 50,000 years old, which is about 9 times the half-lives of radiocarbon, carbon-14. So, in this class, I had to cut short all the mathematical explanations and derivations, as it would not be possible to understand without pen and paper and just by mouth. I have tried to keep it as basic and simple as it could be. I hope the students enjoy this class and understand the importance of radioactivity. Signing off, Dr. Yoshiko Bailung, Department of Physics, Kuala College.